Welcome back after a brief period of inactivity. So today we are going to start number theory from the book Elementary Number Theory by David M. Burton. So in this book, the first chapter is named Some Preliminary Considerations, and the first section is Mathematical Induction. Now we already know about mathematical induction. We have seen what it means, what it is, and how it can be used to prove some statements that involve natural numbers. But again, to see what mathematical induction is from the point of view of the author, and also to see how it is related to things in number theory, we are going to have a look at it. Now the theory of numbers, the author starts things like this. The theory of numbers, in its elementary aspects at least, is about, it's a study of properties of things we know as the integers, and more particularly positive integers, that is these numbers 1, 2, 3, etc., also known as the natural numbers. Now after this, the author writes a line which often will be, it's highly likely that it will be overlooked, but it's actually very important. We shall make no attempt to construct integers axiomatically, assuming instead that we are familiar with many properties of them. Now this is the place where I should perhaps add some words of my own. It's about the other book that we have been studying for quite some time now, Analysis 1 by Terence Tao. In that book, we have actually constructed integers axiomatically, and not only that, we proved many elementary properties of integers from those axioms. So that is one thing. And the other thing you may notice here is that Burton is calling these numbers natural numbers. However, tau includes 0. That is, for tau, 0 is also a natural number. Now what is this discrepancy? It's not something that is very serious. It's just a matter of calling or not calling 0 a natural number. So when you are studying a given text in mathematics, a given book or a given lecture note, whatever it is, you have to make sure what the set of natural numbers means, whether it includes 0 or it does not include 0. It's just that. It's not going to make any difference whatsoever in the mathematics, resulting mathematics. Okay, now the situation is this. We are supposed to know many properties of integers, and we already know many of them. Many elementary properties we already know. Now next we are going to state one very important property from where things will start, and this one has a name. It's called the well-ordering principle. Let me state the principle first, and then we will discuss. Any non-empty set S of non-negative integers has a smallest element. That's what the principle says. That is, there exists an element A in S such that A is less than or equal to B for every element B in S. Now, okay, so it just says this. You have the set of non-negative integers and S is a subset of this set. So S is, elements of S are coming from this set. How many, which elements, we don't know. The only thing we know about S is that it is non-empty, that is, it has at least one element from this set and only elements from this set, because S is a subset of this set. Then S has a smallest element, that is, there is some element A in S that is less than or equal to every element of S. Less than or equal to, we keep this possibility to, for the case where you can take A, because you are saying that this is true for every element in S. So we cannot take strict inequality. So that's what the principle is. Now those of us who have gone through Tau's analysis 1, and that is those of us who have gone through the axiomatic construction of integers, they will say that we have not come across this principle. Where is it in Tau's book? The fact is that it is there in chapter 8. We have some time before it comes to us. Okay, we will see that it's there, and it comes as a consequence of the axioms using which we constructed the integers, that is the piano axioms. If you are not getting what I am saying, don't bother about the parts of this discussion where we talk about Tau's analysis 1. You just look at these things. So this is something that is true and we are supposed to know. In what sense is it true? We will discuss about that later. Why do we know that it is true? So let's just leave that aspect for now, and we take it for granted that this is true. If you consider any non-empty subset of the set of non-negative integers, it must have a smallest element, which you can naturally understand. Okay, you can feel why it happens. You can, for example, take some particular subsets of this set and see for yourself that you will always find a smallest element. That is by no means a proof of the fact, but it will give you an idea of why this is supposed to be true, or why this should be true. Okay, so this is well ordering principle. Another way of expressing this is also this, that the set of natural numbers or the set of non-negative integers is well ordered. When we say that a set is well ordered, it has this property, that any non-empty subset has a smallest element. Now, an immediate consequence, there are some consequences of this well ordering principle. One immediate consequence is the Archimedean property. Okay, so that is our first theorem. Let A and B be any two positive integers. Then there exists a positive integer n such that NA is greater than or equal to B. The statement is clear. If you are given two positive integers, then you will have another positive integer n for which this inequality will be true. So what this inequality says is basically this: you may choose B to be quite large and far larger than A, but still you will have a positive integer n large enough such that if you multiply n and A, the resulting product will not be less than B. It will either be equal to B or it will even exceed B, greater than B. Now, this is not the most general version of this property, which is called Archimedean property, but in this restricted sense, we need only this much in this book. So let us see how we can prove this from the well ordering principle. So we assume that, suppose that this is not true. Suppose that the Archimedean property being true means what? That for every pair of positive integers A and B, we will find at least one n for which this inequality is true. The negation of that statement is the existence of at least two positive integers for which this will not happen. That means for which no n will work, such that this inequality is true. So we are supposing that negation. Suppose that there exist positive integers A and B such that NA is less than B for all positive integers n. Okay. Then the set is defined like this: B minus NA where n is a positive integer consists of positive integers only Okay, now what is the set S? S is the set of all integers that look like this: B minus NA, where B and A are of course fixed. This B and A that we have supposed that they exist, and N is varying. N is varying over all positive integers. Okay, so the smallest value of n is 1, then n can take the value 2, 3, etc. So this set S has such integers, and because of the way we have supposed the existence of A and B, whatever n may be, b is always greater than na. So that means b minus na is a positive integer. So all the elements in S are positive integers. So S is a subset of the set of positive integers, and in particular non-negative integers also. Note that S is non-empty. S is non-empty because in fact S will consist of S will contain infinitely many elements. You take n equal to 1, you get one element. You take n equal to 2, you get another element, like that. So by the well ordering principle, S has a smallest element b minus ma, where m is a positive integer. So since S is a subset of the set of non-negative integers, in fact the set of positive integers actually, and S is non-empty, so it will have some smallest element. But the elements in S look like this, they are of this form. So for some positive integer m, this will be the smallest element of S. Now, since m plus 1 is also a positive integer, b minus m plus 1 times a must belong to S, because it has that form to be in S. But b minus m plus 1 times a is actually equal to b minus ma minus a, and this is strictly less than b minus ma. The reason for this strict inequality is the fact that a is a positive integer. So we are subtracting a from this, so clearly the result will be smaller than the original number from which we are subtracting. But then what are we getting? What conclusion are we drawing from this situation? We have chosen b minus ma to be the smallest element in S, but now we have got another element b minus m plus 1 times a also in S, but it is smaller than the smallest element, so that is a contradiction. But this contradicts the smallest nature of b minus ma. So that means our initial supposition is wrong. So for any positive integers a and b, there exists a positive integer n such that na is greater than or equal to b. So this Archimedean property is also going to be useful to us when we start solving problems in number theory, and in many theoretical situations also it will be quite useful. Okay, now we come to the main theme of this section. Theorem 1.2. First principle of finite induction. And the statement is something you already know. Let S be a set of positive integers with the following two properties. A, the integer 1 is in S. B, whenever the integer k is in S, comma, the integer k plus 1 is also in S. S has these two properties, and S is a set of positive integers. That means S is a subset of the set of all positive integers. S may or may not have all the positive integers as its elements. We don't really know when we are stating this theorem, at least the hypothesis. I mean, so far we don't know what S is. The only thing is we know is that S has these two properties, and S is a subset of the set of all positive integers. But then the conclusion of this theorem is precisely that. It says that S is actually the set of all positive integers. Then S consists of all the positive integers. And we are now going to prove this result as a consequence of, again, that well ordering principle. Okay, but let me feed this some ink before. prove so we want to show that S is equal to the set of all positive integers. Suppose that is not true, then there will be positive integers not in S, and we are considering the set of such positive integers t. Okay, let t be the set of those positive integers that are not in S. Our supposition is this. Suppose T is non-empty, that is, there is at least one positive integer that is not in S. Then T is a non-empty subset of the set of positive integers. So by the well-ordering principle, T will have a least element T has a smallest element, say A. Now this A is a positive integer that is in T. Okay. However, from condition A, we already know that the integer 1 is in S, and according to our definition of T, T is the set of precisely those positive integers that are not in S. So that means A cannot be equal to 1 because A is in T and 1 is in S, and T and S are disjoint, they don't have any element in common. So since 1 is in S, we must have A greater than 1 because 1 is the smallest positive integer and A is some positive integer that cannot be equal to 1 because A is not in S and 1 is in S. Okay, so A is greater than 1. Then A minus 1 is a positive integer that is less than A. A minus 1 of course is less than A, but since A is greater than 1, A minus 1 at the same time is also a positive integer. Thus, A minus 1 cannot be in T. Why? Because it is smaller than the smallest element of T. A is the smallest element of T. So A minus 1 cannot belong to T because then it will be smaller than every element of T. And as a consequence, hence A minus 1 is in S. Why though? Because you see, every positive integer is either in S or in T, because T by definition is the set of those positive integers that are not in S. So that means if you take the union of s and t, you will get the set of all positive integers. So because a minus 1 is a positive integer, so it has to belong to either t or s, but it does not belong to t, so it has to belong to s. But then by condition B, if something belongs to s, then if you add 1 to that number, the resultant also must belong to s. But then a equal to a minus 1 plus 1 should belong to s, and it will be a contradiction. So that means this supposition is wrong, so t cannot be non-empty. So that means the set of those positive integers that are not in S is empty. In other words, S has all the positive integers. Hence, that completes the proof. Okay. Now, using this principle, let us prove a statement about positive integers. That for every positive integer n squared is equal to n times n plus 1 times 2n plus 1 divided by 6. So we start the proof like this. Let S be the set of all positive integers n for which the given formula, means this one, is true. Our aim is to show that S is the set of all positive integers, so that for every positive integer this formula will be true. And the method, of course, is by the first principle of finite induction. Note that one square is equal to 1 which is also equal to 1 times 1 plus 1 times 2 times 1 plus 1 divided by 6, because here one of the factors will be 2, the other factor will be 3, so ultimately we will get 1. And so and so 1 is in S. So condition 1 in the statement of theorem 1.2 is true. We have proved that 1 is in S. Assume that some positive integer k is in S, that is then this is equal to, now this is our assumption, this is the assumption that the positive integer k is in S, so we can use it here for this part of the sum. Ignoring the last term, the rest of them give us this left hand side. So this is equal to k times k plus 1 times 2k plus 1 divided by 6 plus k plus 1 square. Okay. Now what we do, we take k plus 1 divided by 6 common out from these two terms, so we will be left with k times 2k plus 1 plus 6 times k plus 1. This will be equal to 2k square plus k plus 6k is 7k plus 6, that is equal to k plus 1 divided by 6 times, okay, so this is 6 times 2 is 12. 2k square plus 4k plus 3k plus 6. This is equal to k plus 1 time divided by 6 times. If we take 2k common out from the first two terms, then we will have k plus 2. We take 3 common out from the last two terms, we will have k plus 2 times now we can take k plus 2 common out. So this will be equal to k plus 1 divided by 6 times k plus 2, and we will be left with 2k plus 3. And let me write it in another line. This can be written as, this factor is k plus 1, let's just keep it like this. K plus 2 I can write as k plus 1 plus 1, and 2k plus 3 can be written as 2 times k plus 1 plus 1 divided by 6. Now you look at the final form. It's just like this one, except if you replace k with k plus 1. So that means our formula is also true for k plus 1. This implies k plus 1 also belongs to S. So that means the second condition in the principle of finite induction is also true for S. So by the first principle of finite induction, S consists of all the positive integers. That is, this is equal to n times n plus 1 times 2n plus 1 whole divided by 6 for all positive integers n. So this way, using theorem 1.2, we can prove statements about positive integers, sometimes about non-negative integers also. Okay, now some more, having done this thing and showing how induction can be used, which probably you already know all these things, and you also don't write this much while carrying out a proof by induction, but for the sake of showing it in its full glory, or with all the details, for at least once we did it this way. Now there are some discussions about this. Discussions about this method of induction. Although mathematical induction provides us with a standard technique for attempting to prove a statement about positive integers here. One disadvantage is that it does not aid us in formulating one. That is, once a statement is given which someone is claiming to be true, then it can be proved to be true using mathematical induction, provided of course one can actually carry out the proof. I mean, it's not the case that if you are given something, you start mathematical induction algorithmically, as if some computer is doing it. There is a program that can be written where one shows that 1 is in S, then if k is in S, then k plus 1 is also in S. Yes, those are the steps that you should take in order to show by induction that something is true. But in proving that 1 is in S, it's not always the same thing. I mean, what I'm trying to say here is that to prove that 1 is in S, different situations will require you to formulate different kinds of strategies. Just proving that 1 is in S may in itself be a difficult job, but at least you can attempt to prove something by induction in this way. But induction does not tell you anything about why, I mean, how someone comes up with such formula in the first place. For example, if this right hand side is not given to you, then you cannot use induction to guess what the right hand side is. Okay, so that's what they are saying. Although mathematical induction provides us with a standard technique for attempting to prove a statement about positive integers, but the disadvantage is that it does not aid us in formulating any such statement. That has to be there. Okay, by some means someone has to be able to guess the statement first, and then using mathematical induction one can attempt to prove it. Of course, we can make an educated guess that something is true. that the guess is indeed true. For example, consider the following computations or equalities, whatever you may call them. And the list is this. Seven, 15, 31, 63. Okay, so we are adding consecutive integral powers of 2. The first one is 2 to the power 0, then 2 to the power 0 plus 2 to the power 1, and so on. And the pattern is like that on the left hand sides of all these equalities. But can we guess what the right hand side is? We seek for the numbers on the right hand side. After some reflection, one may notice this pattern. One is 2 to the power 1 minus 1. After 1 we have 3. 3 is 2 square minus 1. 7 is 2 cube minus 1. Then 15 is 2 to the power 4 minus 1. 31 is 2 to the power 5 minus 1. 63 is 2 to the power 6 minus 1. Okay. How one comes up with such an observation is heart to say, but experience helps. The more you deal with these things, the more likely you will be able to find something, some such pattern. It's not a guarantee that you will find something, of course, I mean in every situation, but the more you spend time with these things, the more likely you are to find something. It seems that for every positive integer n, we should have this. Is this true? So that is the guessing part. Okay, the guessing part has nothing to do with induction. But now, to verify that this is actually the case for all positive integers, we can try an induction proof. For which the above formula holds. Now, one here in this context, this one is the left hand side when n is equal to 1, because if n is 1, then this term is also 1, this term is also 1. So that means in this sum there is only one term, that is 1. 1 is equal to 2 to the power 1 minus 1. In fact, that's what we have seen here. Which implies 1 is in S. Assume that the positive integer k is in S. Then this is true. And this is equal to, for the first part except the last term, we can use this formula. So this is 2 to the power k minus 1 plus 2 to the power k, this one. So we have got 2 to the power k's. So 2 times 2 to the power k minus 1, which is 2 to the power k plus 1 minus 1, which you can see is just the formula that we guessed when we have k plus 1 in place of k, where this 2 to the power k is actually 2 to the power k plus 1 minus 1. This is in S. So by is it first print? The name is so big. If we want, we can, because I tend to forget things pretty quickly. First principle of finite induction, yes. Or you can say theorem 1.2 also in the context of this book. All the positive integers. So that just proves that this formula is true for all the positive integers, because according to our choice, S is the set of those positive integers for which the formula is true. Okay, now we make a remark that will simplify life a little. You may have noticed, okay, so we have gone so far with 2 induction proofs, and in both of them we are writing S. We are taking S to be the set of those positive integers for which the given formula is true. There is no need to write these things. So it's about that we have this remark. When writing induction proofs, we shall usually shorten the argument. By eliminating all references to the set S. And proceed to show simply that the result in question is true for the positive integer 1 and is true for the integer k plus 1 whenever it is true for k. So we won't say anything about S from now on. Okay, now some warning from the author. We should inject a word of caution here. Neither of the conditions is sufficient alone. That is, we need to show two things now. That one is in S, and when k is in S, where k is a positive integer, then so is k plus 1. The first one is condition A, the second one is condition B. None of them alone can give you a proof that S is the set of all positive integers. And in this context, condition A, or rather the proof of condition A, is called the basis for the induction. That is, it is the base on which the whole induction rests. And the proof of B proof of condition B is called the induction step. And the induction process itself has been likened to a series of dominoes that have been arranged in a manner where they are standing on edge, and there is a first domino. If you knock that, that will knock the next domino in line, which in turn will knock the next domino in line. So all the dominoes will fall. Okay. And in fact, that's what the author is saying. The induction has been likened to an infinite row of dominoes. Standing on their edge. And are arranged in such a way that if one falls, it knocks down the next in line. it's like this. And they go on like that. So if one falls in this direction, it will knock this one over, which in turn will knock the next in line, and that effect will propagate down the line, and ultimately all the dominoes will fall. Of course, in this sense, it will take infinitely long for the whole line to fall, but just for the sake of analogy, you can understand what I am trying to say here. This is the case that 1 belongs to S, and whenever some domino k belongs to S, that is, if k falls, then k plus 1 also falls. Okay, so the collapse will start from here and it will propagate along the line. The next in line. If the first domino does not fall, that is, if there is no basis for the induction, or if the spacing in between them is too large, that is, if the induction step fails, then the full line will not fall. Complete line will not fall. Okay, so that is the nature of induction. Okay, now here is again one more important point. The validity of the induction step is not dependent on the truth of the statement one is trying to prove by induction. That is, one may try to prove a wrong formula by induction, not starting with a basis. That is, one does not care about basis, but the induction step happens to be true. That is, it may be the situation that you are able to carry out the induction step without looking at any basis, and the formula is actually wrong. So that can also happen, and clearly then nothing is proved. And one such situation is this. Let us look at the false formula. One plus 3 plus 5 etc. That means all odd positive integers plus 2 and minus 1 is equal to n square plus 3. Assume that the above formula is true for some positive integer k, that is equal to k square plus 3. Then what is the next odd integer? 2k minus 1. The next integer is 2k, which is even. After that 2k plus 1. So this is equal to, using this assumption, k square plus 3 plus 2k plus 1. But this k square plus 2k plus 1 gives us k plus 1 whole square plus 3. So you see that this induction step is actually it works out. Okay. However, the formula itself is false. There is in fact no positive integer n for which this formula is true. You can clearly see if you take n equal to 1, because it is saying that this is true for all positive integers n. Okay. If you take n equal to 1, the left hand side is 1, whereas the right hand side is 4. So it's a false one. So here you see that if one simply verifies only condition B, then it's not a guarantee that the given formula is true. Now there is a variant of the first principle of finite induction, that is Theorem 1.2. In this, we keep condition A intact, but replace condition B. I need some ink. with a new condition b prime. If the positive integers one, two, etc. up to k are all in S, then so is k plus 1. So in this new condition we are not considering only the hypothesis that k is in S, but all positive integers starting from 1 all the way up to k, all of them are in S. If that happens, then k plus 1 is also in S. Why do we need this variation? I mean this another version of induction principle. There are some situations where to carry out the induction step, the knowledge of k being in S alone is not sufficient. We in fact need something more. We need all the positive integers less than or equal to k to be in S. Then only we can conveniently carry out the induction step and claim that the given formula is true for all positive integers. And the proof of this one is also just like the proof of theorem 1.2. So in this proof again you assume that T is let T be the set of all positive integers that are not in S. But keep in mind, now our S has these two conditions, where the first one is saying 1 belongs to S, but the second one is this. And you suppose that T is non-empty. Okay, so this one I am not going to write, I am just going to show the argument sketchily and you supply the missing details. That means you write the proof systematically. So we have assumed T to be the set of all positive integers that are not in S, and this is our supposition that T is non-empty. Then by the well ordering principle, T will have a least element, a smallest element, just like before. Let that element be A. Now since 1 belongs to S, again like before, A is greater than 1. So A minus 1 is a positive integer that cannot be in T. And in fact, that's why none of these positive integers are in T. So all of them must belong to S. And then by this new condition B prime, we claim that hence A minus 1 plus 1, which is A, it must also be in S, which is a contradiction because A is the smallest element of T and T and S are disjoint, they cannot have any element in common. So this supposition is wrong, and hence S is the set of all positive integers. Okay, so this part I am leaving to you. Then conclusion is saying consists of all the positive integers. prove it. Our formulation of, and this one is known just like that was the first principle of finite induction. This is the second principle of finite induction, where we replace B with B prime. Our formulation of both the versions of induction has been such that the induction starts from 1. In both the first as well as the second principle, 1 belongs to S. That's how we start the induction. But one can generalize this by starting from any positive integer n naught. If this version of induction is you are using this, then the first principle will look like this. Let S be a set of positive integers that satisfies these two conditions. Condition A is n naught is in S and condition B is this. If k is any positive integer greater than or equal to n naught and k is in S, then this implies k plus 1 also is in S. Then the conclusion, however, is not that S is the set of all positive integers. The conclusion is that S is the set of all positive integers greater than or equal to n naught. And if you modify the second principle like this, then the first condition will be this and the second condition will be this. If all the positive integers n naught plus 1 etc. up to k, where k itself is some positive integer, if they belong to S, then k plus 1 belongs to S. Then also the conclusion is same. S is the set of all positive integers greater than or equal to n naught. Okay, and these versions also like this can be proved. They can actually be proved using the well ordering principle. Now you may be wondering about one thing. If you have been following Tau's analysis and our development of the set of integers there, in Tau's analysis, the view is that mathematics starts from the piano axioms, and it actually starts from the system of natural numbers, where the principle of induction, although there it starts with 0, but like this remark that it can start from anywhere, the induction principle is actually an axiom which has been taken to be true. Okay, its truth does not depend, in Tau's treatment of things, the truth of the induction principle does not depend on something more basic than induction. Okay, we assume it to be true. Of course, it's just an assumption, and then using it as an axiom, we do everything else. We In fact, by now we have actually developed the system of real numbers also. And here it seems like there is something more basic, the well ordering principle. From there we have proved the first principle of induction. And if you take n naught, although here we have taken n naught to be a positive integer, but if you want, you can, do you see that in place of 1 in the first principle of induction, you can actually take 0 and carry out the proof. Of course, for that you will need a slightly more modified version of the well ordering principle, one that has 0 in, I think in the well ordering principle we have 0, no? Because the statement of the well ordering principle says that if S is a set of non-negative integers, yes, and S is non-empty, then S has a least element, yes, so you can start things from 0. So what I am trying to say here is this: you have, on one hand you have induction principle, starting from 0 or starting from 1, that does not matter. We are, for the time being, we are not distinguishing between them. We have the induction principle, and in Tau's analysis everything is starting from here, and this has no underlying proof, okay, for its validity. However, here in this book we have the well ordering principle, and we have proved the induction principle as a consequence of the well ordering principle. Does it mean that this is something more fundamental? And if so, why did Tau not start with well ordering principle? The answer to this is that actually there is nothing like this is more fundamental than this, because one can prove the well ordering principle also from the induction principle. In fact, when we come across the well ordering principle in Tau's analysis in chapter 8, we will prove this, okay, that this implies this. Here we have proved that this implies this. However, it just shows that as far as an axiom goes, whose proof, which is something that you just take for granted simply because it's easy to believe, it's so easy that one can believe, these two statements have the same status. If one is true, then so is the other. They are logically equivalent. Either they are both true or they are both false. Note that this does not say anything about the absolute truth of any one of them. It just says that the conditional truths, conditionally the statements are true. If one is true, then so is the other. Because that is the, what to say? That's how you use axiom. You have to have a base somewhere. If you are going on asking why is this true, okay, this is true because of something else. Why is that thing true? That is true because of something yet more fundamental. Then you won't stop going down. You have to decide on something which is so basic that it's easy to believe that it is true as the basis for your everything. And then from that point you have to develop things. So Tau has decided to use this one as the basis for his development of mathematics. But here the author has decided to use the well ordering principle, because that way things are much easier, okay. So any one of them can be used as an axiom from a logical point of view. Now comes another aspect of induction, namely using it not as a tool for proving statements but as a tool for defining things, and that is this. is not only used as a tool for proving statements, but also as a tool for method or tool is same thing. For example, this symbol pronounced as n factorial is usually defined like this. 1 factorial is defined to be equal to 1 and n factorial is defined to be equal to n times n minus 1 factorial. For all integers n greater than 1. Okay, so that when n is greater than 1, n minus 1 is still a positive integer. This pair of conditions, that means this is one condition, this is another condition, provides a rule whereby the meaning of n factorial is specified for every positive integer. N. Thus, for example, 1 factorial is already by definition 1. Okay. 2 factorial, since 2 is greater than 1, so it is by definition equal to two times 2 minus 1 factorial. This is equal to 2 times 1 factorial, but 1 factorial is 1, so this is equal to, that means this is 2 times 1. Like that, 3 factorial is 3 times 3 minus 1 factorial, that is 3 times 2 factorial, so that means this is 3 times 2 times 1. Okay, so this way we can know the meaning of n factorial for every positive integer n. Continuing like this, one we get n times n minus 1 times n minus 2 etc. like that, 3 times 2 times 1. Okay, but where is induction being used? You can okay, we have seen all these things already, right? We have seen things being defined this way, and we have got a habit of saying that we have used induction to define it. Does it really make sense that we are using induction to define something? Can you prove that yes, this is well defined by induction? Because that question arises. Is it well defined by induction? Does this or do these two conditions really give us a unique meaning of n factorial for every positive integer n? That is a legitimate and serious question, and that question has already been answered in the very beginning of analysis 1 by Tao in the form of the principle of recursive definition. We have already come across that. We have in fact proved that also, and using that we have started our development of the system of natural numbers. There, using the principle of recursive definition only, we were able to define addition and multiplication in the set of natural numbers, and things went ahead from there. Okay, so it's an issue that will be left untouched by the author here. So that's why he says induction enters in showing that n factorial as a function of positive integers exists and is unique. That is, there exists exactly one function that satisfies these conditions. Okay, and that statement has already been proved by us, although we won't discuss that here in analysis 1. We have already all the things required to prove this. However, we shall make no attempt to give an argument but we don't need an argument, because from Tao's result this is already following. That's why I started analysis 1 in the very beginning. It has most of the things that you will find in other books being overlooked. It will be convenient to extend the definition of n factorial to the case n equal to 0 by stipulating 0 factorial to be equal to 1. That is, we are defining the symbol 0 factorial to be 1. That's what it means. And lastly, there is one example that shows that the second principle of induction is also necessary, that there are situations where you the first principle will not give you it's not well suited. Such situations occur. Consider the following sequence: 1, 3, 4, 7, 11, 18, 27, etc. And this sequence is, if you define it that way, that is using induction, this sequence looks like this: A1, A2. I'm writing these things sketchily, okay? A3, etc. Where A1 is defined to be equal to 1, A2 is defined to be equal to 3, and everything else, if you look carefully, you will see that every other term is a sum of the the sum of the previous two terms. 4 is 1 plus 3, 7 is 4 plus 3, and so on. So that means an is an minus 1 plus an minus 2 for all positive integers n greater than or equal to 3. Okay, now this sequence has a name known as the Lucas sequence. There are other sequences like this which follow the similar rule of the terms being the sum of the previous two terms. One such sequence is the Fibonacci sequence, which starts with two ones instead of 1 and 3. Now the claim here is that an is less than or greater than 7 by 4 whole to the power n, okay, for all n greater than or equal to 1. In the proof of this, we need the second principle of finite induction. The proof, let me just quickly tell you how it can be done. First, you show these two things. This is A2, this is A1. In fact, one can easily show that this is the case. 4 square is 16. 16 times 3 is 48. But here you have 7 square, 49. So 49 is greater than 48. And this one is of course true. 7 is greater than 4. So that means the statement this inequality is true for n equal to 1 and also for n equal to 3. Then what you do, you assume k to be a positive integer greater than or equal to 3, and you assume that the inequality is true for 1, 2, 3, etc. up to k. Okay, then you have to prove it for k plus 1. Then ak plus 1 by definition is ak plus ak minus 1. Now since k and k minus 1 are both lying in this range for which the inequality is true, so the first term will be less than this and the second term will be less than this. Then from this one will try to show that ak plus 1 will be less than 7 by 4 whole to the power a plus 1. That part I am not doing here in this video, that we will see in the next video. So with this I end the video here. So we will complete these things and we will go to the exercises. So that's all for tonight. If you have any doubt regarding this or any other things related to mathematics, you can comment in the comment section below. So signing off from a mathematical room, this is Lucifer. Have a nice night.